Hi, this is Kristen Phillips, and my presentation number 2. I chose to explain Theorem 6.5.8. So, what is Theorem 6.5.8? In our notes, it said that the Galois group of the polynomial p of x is the same as x to the fifth minus 6x plus 3 over q is S5, which is not solvable, and then therefore implies that p of x is not solvable by radicals. So when I first read this theorem and the proof that went along with it, I thought a couple things that we needed to make sure that we understood to make sure that I fully understood this theorem, and the idea of not solvable by radicals really stuck out to me. In order to understand this theorem, I needed to know what this phrase meant. So from there, I tried to further my understanding as to what not solving by radicals meant. So solving by radicals, what does that mean? So if we have a polynomial that is solvable by radicals, that means we can obtain a solution of the equation of the polynomial equal to 0 by the operations of addition, subtraction, multiplication, division, and then the extraction of the nth roots. So from here, I kind of understood what addition, subtraction, multiplication, division of that meant, but then the extraction of the nth roots, I just wanted to make sure that I was understanding that correctly, and the extraction of the nth roots meant that we need a succession of radical extensions or a tower of fields. So that's what it means for the polynomial to be solvable in radicals, but our theorem states that it's not solvable in radicals, which means that this solution is not possible using the operations of addition, subtraction, multiplication, division, and or the extraction of nth roots. So from there, I went to look at, or to verify that the polynomial x to the fifth minus 6x plus 3 is irreducible over q. So at first I thought, okay, well, let's assume that p of x is irreducible. What does that mean? If it is reducible over q, what does that mean? Well, since it's a quintic, there are a couple of options that it could have in terms of it to be irreducible over q. One would be that p of x would be able to be factored in terms of 5 linear factors, which that's not the case for this polynomial. So then we could move on to see, okay, well, p of x could then be a product of 3 linear factors and then an irreducible quadratic. That's also not the case here. So then we moved on to number 3, where p of x could be the product of 2 linear factors and an irreducible cubic. Again, still not the case. So then our two options, 4 and 5, were either that p of x is the product of 1 linear factor and an irreducible quartic, or p of x is the product of 1 linear factor and 2 irreducible quadratics. Well, p of x does not have a root in F5, where F5 is a finite field with 5 elements. So therefore, none of these 5 scenarios are possible. Okay, so that leaves us with one other option, assuming that p of x is reducible. P of x is the product of an irreducible quadratic and an irreducible cubic. If that was the case, then it would be reducible. But we know that our finite field has 25 elements, is the splitting field extension for quadratics over our finite field with 5 elements. So if p of x has an irreducible quadratic in its factorization, then p of x would have a root in the finite field of 25 elements. This is not true. So therefore we can conclude then that this polynomial is irreducible and our assumption was incorrect. So we have shown that x to the fifth minus 6x plus 3, our polynomial, is irreducible over q. So next we need to determine the roots of this polynomial, and specifically what are the two complex roots. So upon some resources, I found the real roots, and I found these real roots. I can just use my graphing calculator to determine these real roots. Here were my 3 real roots, which left my complex roots as 2 conjugates, or a pair of conjugates, negative 0.118 plus 1.5875i, and then your 5th or your second complex root was negative 0.1181 minus 1.5875i. And the proof states, and we can clearly see it here based on how these complex roots are written, that these 2 complex roots correspond via conjugation. And then this tells us that our Galois group of this polynomial must contain a 2-cycle. And then we get to the next part of this proof. So if we let lambda be a root of p of x, then our degree is 5. Our degree over q is 5. This implies that the order of our Galois group must be divisible by 5, and therefore an element of order 5. So we can say that's a 5-cycle. Well, back in chapter 5, we saw theorem 5.2.13, which stated that if a subgroup of Sn contains the 2-cycle, 1, 2, and the n-cycle, then H is in Sn. Well, we already saw previously that because these 2 complex roots are conjugates, that it is 2-cycle. And because of our degree, it's divisible by 5, which makes it a 5-cycle. So then we can conclude that the whole group S5 is generated. So that explains the proof a little bit further as to why our polynomial is not solvable. So from here, I chose to look a little further at an example and determine whether another polynomial of a quintic polynomial was not solvable also by radicals. So I took a little bit of a different approach than I did in the previous example. So I said, okay, let f of x equal x to the 5th minus 16x plus 2. Let's assume that it's not solvable by radicals, or let's show that it's not solvable by radicals. So I decided, okay, let's compare this to a polynomial that is solvable by radicals. So we have x to the 5th minus 16x. The product of a linear, a quadratic, and then an irreducible quadratic. So this g of x here has 3 real roots. The real roots are 0, 2, and negative 2, and then 2 complex roots. Well, f of x and g of x are related because f of x is g of x plus 2. Thus, g of x has, like we stated, has 3 real roots. And by determining g of negative 1, or finding when x equals negative 1, we see that g of x is 15. If we say x equals 1, we find that g of 1 is negative 15. Thus, we see that x to the 5th minus 16x plus 2 also has 3 real roots, and therefore is irreducible over q. And therefore, we can conclude that f of x, our initial quintic polynomial, x to the 5th minus 16x plus 2, is not solvable by radicals, meaning that we cannot write this in terms of operation of addition, multiplication, division, and subtraction, or by using the nth roots of unity. So this is another example of how our quintic was not solvable by radicals. So again, just to recap the entire theorem that we looked at here, the polynomial over q is S5, which is not solvable. And I think the biggest thing that I got away from this is really fully understanding what it meant to be not solvable in terms of radicals and what the extraction of nth roots meant. So there was my explanation of theorem 6.5.8. Thanks for listening.